Well, ladies and gentlemen, a very good morning. Come on, this should be a little more louder. Good morning. Well done. Okay, welcome to Slash N 2016 Day 2. This is the fourth edition. Yesterday we had a power-packed day, day number 1, and today we are all set to rock day number 2. Well, are you ready to slash in? Okay, let's start with our first speaker for today. We have Vijay. Vijay is CTO and co-founder at Hue. Prior to co-founding Hue, Vijay was a research scientist at IBM Research for 2.5 years. And today he's going to talk to us about visual enrichment and visual interactions to find your favorite fashion. Ladies and gentlemen, put your hands together and welcome Vijay.
So, a first word of caution, some of these slides I have prepared last night. So, with you, I'm also seeing some of these slides for the first time. So, who are we? We are a fashion discovery and search app. We are essentially indexing lots of inspirations and lots of products from different points on the web. We get data from fashion blogs, we get data from social media, we also get data from e-commerce portals, and we are organizing them at one place. We are quite early in our journey. We released a mobile application in September this year, and we have about 10,000 users. Over last few months, I have been talking to a lot of fashion consumers as well as fashion product managers. And we have discovered a few problems that I'm going to share with you before I jump into the actual technology problems. So from the consumer perspective, what we have found is that fashion shopping is fragmented, it is not organized, and it is many a times cumbersome. And hence, millions of shoppers significantly overspend their time and money when they have to shop for fashion. So that's the problem that we are solving. So what do I mean by fashion discovery being fragmented? Indian fashionistas alone generate more than 1 million looks every single month. And from the consumer perspective, there are more than 15 million products that consumers have access to. And when consumers have to discover and search for fashion, they have to hit this deluge of multiple catalogs to discover and search for their most favorite fashion item. And all this data is not organized properly. So for instance, there are millions of inspirations that exist on the web, but these are not linked to the products that you can actually shop. These are the top 3 fashion shopping apps in India. And what I have done is I have taken Google Trend keywords and have put them into these search bars. And as you can see, the performance is not that great. I mean, I'm sure all of us are working towards solving these problems. But I feel these problems occur because products are not organized and indexed to answer real consumer intents. And because of such lack of indexing, more than 30% of the products across different e-commerce portals are either duplicate or very similar. Essentially, the same product appears on different touch points, but it appears at different price or from different merchant or from different seller. And finally, most of us shop on e-commerce portals. When you have to shop for a laptop or a phone, you can put a few simple filters and then you can pretty much get the item that you want. But what we have realized, and this is something that consumers have told us many times, is that it's not exactly, it's not easy to just set a few filters and then get your most favorite fashion item. Fashion is something that is very visual, it is very interactive, and what we have today is a single-step process which is not interactive and which gives you the entire catalog when you search for it. So how do we solve these problems? If we have to solve these problems, we have to index a lot of looks from different parts of the web and make them shoppable. We also have to enrich products with tags or intents which are more consumer focused. And we also have to have lots of relationships between these products so that it becomes easier for people to navigate through all these products. So it's essentially a problem of indexing and linking all this data. So that is what we are building at our company. We essentially sit at the intersection of visual web and e-commerce and provide consumers that single stop destination where they can discover and search fashion. And at present, we are focusing on women shoppers in the age group of 18 to 30 from tier 1 and tier 2 cities. So how are we solving this problem? Today on our platform, we have more than 30 fashionistas with whom we have partnerships. And we get about 100K inspirations onto our platform. We also have affiliate relationships with 15 retailers. And we have more than 2 million products onto our platform. So it's a single stop engine for consumers. Using deep learning and deep image matching, we have linked thousands of these inspirations to products from different merchants. And we have created a fashion magazine which gets personalized as you start interacting with it. Again, using visual intelligence, we have created links between a product. So these links are like duplicate or similar or complementary. So for instance, using duplicate relationship, we essentially give best price experience for absolutely any product that we have on our platform. And you can see a few examples here. And again, using visual intelligence by just looking at the images, we have enriched products with consumer-focused tags like college or Diwali, evening, party, or so. So, for instance, if you search for a college tops, you will get tops which are most suitable for college. And not just that, you can interact with the search results. And as you interact, the search engine pulls out the most similar items for you so that you can arrive at the product that you want to buy faster. So to summarize the problem and the solution, we are going from being fragmented to being aggregated. We are going from being unorganized to organized. And in terms of search, from being cumbersome to be easy to navigate. And our promise to consumers is very simple. You will save significant time and significant money if you are using our app, right? So for this talk, I'm going to focus on how we are enabling best price for every product and most relevant variety for every intent. So how are we doing this? We get catalogs from different merchants, and we are essentially visually enriching them. And we are putting all these catalogs into what we call as a visual intelligence graph. So what are the nodes and links in this graph? We have inspiration and product. So these are the two types of nodes that we have in this graph. Inspiration is any inspiring photo on the web. And a product is something that you get on e-commerce portals. So we make these inspirations shoppable by having a matching relationship between these two nodes. Right? To give best price experience, we have duplicate relationships between different products. To make it easier to navigate different products, we add similar and complementary kind of links between different products. And to make search a lot more relevant, we essentially enrich products with different tags. So for instance, in case of products, we have college, casual, outing, these kinds of tags. In case of inspirations, we have evening, Diwali, or your best friend forever's wedding also, so these kinds of tags, right? So I want you to remember this picture of a graph where we have these two nodes, inspirations and products. We have different relationships between these nodes, and each of these nodes is enriched with meta tags. So now the question is, how do we construct this graph, right? Specifically for this talk, how do we do dedupe across millions of products and with a very high accuracy, and how do we enrich millions of products with consumer focused tags, right? So these days in media, on research portals, everywhere you hear about AI, right? So I mean, this task is very simple, right? You can feed a lot of data to AI. It will learn all the juice out of this data, and then it will just output the kind of graph that we want, right? I mean, AI is everywhere, right? So it's in your pockets, it's in your shirts, it's everywhere, right? I mean, as we hear. But reality is not like that, right? So it's really hard to make AI work in practice, and it is not yet at a point where it's a magic wand. So there are lots of pain points that you have to tackle if you have to solve some of the problems that I have described. For instance, how do you get access to data? Not just that, from data to data sets, how do you create data sets at scale? Once you have data sets for a particular task, and you will have to create different data sets for different tasks, how do you choose different deep learning and machine learning models to solve that task? And how do you make them work reliably and accurately? And most likely your task is not going to be solved by just one or two models. You will have to stitch together different models to solve a particular task. So this is going to be the theme of the rest of my presentation. Data sets, deep learning models, and how do you put together different models to solve a problem. So a word of caution, again, these are some of the experiences that we have had at our company, and these are mainly applications of deep learning. We are not doing any research in deep learning. By the way, how many of you have heard about deep learning? How many of you actively work on deep learning? Okay, a fair number, okay. So some of these things could be a very basics for those of you who are working on deep learning. So let's just see a few examples, right? So how do we create a duplicate relationship? Now, first we have to define what do we mean by a duplicate. So the way we define at our company is if two products have to be duplicate, they have to have same photo and they have to come from the same brand. But they could have different price, they could come from different merchants, or they could even come from different sellers. Now, in case of brand, price, merchant, and seller, these things you can easily extract from the text. Although brand is not that easy because many a times it is hidden inside the text. So you have to do deep text parsing to extract the brand. But let's assume that brand, price, merchant, and seller are known to us. So it's a problem of how do we do duplication across different images, right? Now, e-commerce poses different challenges. I mean, most of us know that every product has different types of photos, front, back, side, zoomed in or so. So how do you do dedupe across all these photos? If you consider all such combinations, the scale will become huge. So you have to identify what is the primary photo for a particular product. Not just that, there are lots of variations, right? So there are variations of background, pose, size of the image. You can have different compression techniques. Different e-commerce portals will use different compression techniques. You could also have zoom in and zoom out on the same photo, right? So solving primary photo problem is quite easy, right? You can, we already have data sets in terms of e-commerce photos. You can prepare X and Y examples where X is image and Y is a label. And then you can feed this data set to a simple machine learning model or a deep learning model. And then you can do supervised learning, which it will learn to classify an incoming photo into whether it's a primary photo or not. So let's assume that we know what is a primary photo. Now, how do you solve the problems of getting rid of background, right? So you can do this using image segmentation. So what I have here is input a product photo, and output is a segmentation in terms of what exists inside that photo, what kind of apparels exists, or what kind of footwear or handbag exists also. And how do you achieve this experience? You essentially have to have lots of photos labeled at a pixel level. And then again, you can use, here it's a deep, fully convolutional network that we use. So you can have a lot of this data, and network will essentially learn to reproduce labels for each of the pixels. So that is how a network will learn. And once you do this kind of training, you can get this experience where you can get rid of the background, and you will only have things which are most important, right? So again, I'm going to, so this is like a very quick primer or segmentation. So I'm going to assume that we know which one is a primary photo, and we have done segmentation on lots of photos so that we have the most important properties of the image to tackle. So as I said, dedupe is not a new problem, and it has been in existence since last 15 years. So we thought that let's use some of the existing techniques, right? So deep learning is pretty much a benchmark now when you have to do a dedupe. So we created our own evaluation data set of duplicate images. And you must have heard about AlexNet or KevinNet, or there is XNet, right? So we took one of such models, and we did a forward pass. And what we get is a feature vector in the end. And we also use the same model to compute feature vectors for all the products that we have in our catalog. And then you do a simple search to do a distance-based matching. Mean average precision that we received for a pre-trained model was about 0.05. So roughly what this means is that duplicate is present somewhere in the top 50 photos. And that's not the kind of performance that we want. We want duplicate to be the first match, right? And this is a very poor in that regard. And when we looked at some of the results, what we observed was that there were a few duplicates around the pivot image, but if you have a different pose, or if the photo has a different sharpness, right, these were falling apart. And there were many non-duplicates that were very close to the pivot image. How do you solve this problem? So we felt that, look, the model has not seen the underlying data, so let's train the model so that it fits on the underlying data set. So then we used a supervised learning method, where again we have data sets in terms of categories and the matching products. So we took about 30 categories. We had about 30,000 images, which again we used to train a network in a supervised manner. So essentially you have, again, X, Y kind of examples, where X is a photo and Y is a label. And you are predicting what's the class of this image. And because you have a lot of data set with you already, you can do this. So after doing this, when we observed the mean average precision, it was about 0.25. Again, roughly it means that duplicate is present somewhere in the top 4, but it's not yet up to the mark. And when we saw the results, I mean, we saw that duplicates are coming closer, but there are also a lot of other non-duplicate items which look quite similar to the pivot image were there. So after that, we moved to using some of the advanced deep learning techniques. And we observed that the machine was never trained to see examples of duplicates and examples of what is a non-duplicate. So we thought that let machine learn by seeing these examples. So what you have on the left-hand side are pairs of images, right? So now network is not just going to take a single photo, it is going to take a pair of images. So xy label is here, that x is actually x1 and x2, and y is 1 or minus 1, right? And I have shown example of what is a duplicate and what is a not duplicate. So you feed these two images to a network. So the network has two branches. This is called as a Siamese network. So you do two forward passes, you get two feature vectors, right? And then you use a contrastive loss-based technique where you compute loss so that the loss can be back propagated. So how do you compute loss? So let's say the cos of angle between two feature vectors, if it is towards 1 when you have passed a duplicate, it actually means that network is learning to predict duplicates well, right? But if this cos value is towards 0, it actually means that there is the angle between two feature vectors is high, even though you have marked them as a duplicate, right? So that is how you can compute loss in terms of these examples. And if you see the denominator, you also train for non-duplicates, right? And there is a margin parameter there, which essentially says that, look, if you are marking two examples as not duplicates, and if these are already far apart, I don't need to compute any loss for that, right? But the way you choose this parameter matters a lot. I mean, it can essentially make or break this kind of technique. So a thumb rule is that you can set that parameter to be cos of 2 pi by number of clusters that you can have in your data set. And typically what we have observed is that there are about 14 to 15 clusters that we have in our data set. So after doing this technique, okay, so now we have a technique by which we can train a machine to identify duplicates and not duplicates, right? Do we have any questions here until this point in time? Feel free, if you have any question, feel free to stop me. So this technique consumes thousands of pairs. I mean, unless you show this technique thousands of pairs, it is not going to learn to identify duplicates. In earlier cases, we had access to a lot of data set. How do we create a data set for this example? So one idea is that you can use product images themselves. So for each of the product images, you have lots of variations, right? Front and back photos also. So you can use those as your positive pairs. And for negative pairs, what you can do is you can use a pre-trained network. You remove the top n matches because most likely your duplicate is going to fall there, and then you randomly sample from the rest of the photos, right? So that's how you can prepare a negative pairs as well. But as you can see, a problem here is that a lot of images have different front and back, right? So you can't really use them as duplicates. Now, idea 2 is that you can do a lot of augmentation. So you can take a primary photo and you can do a lot of augmentation in terms of zoom in, different compression techniques also. But danger here is that deep network is going to get overfitted to all your augmentations. And if there is any variation which falls outside this domain, it's not going to work. Now there are lots of academic data sets present which can do a similar search. But this is again not much useful in our case because we want to train network to identify duplicates. So we want to get that MAP to almost towards 1, right? So what we do is we essentially create a labeling interface. So let me just talk about it and then I'll show you that image. So what we do is we use a pre-trained network. We take a top n matches and we give them to manual labeling because most likely duplicate is going to present among those top n or top 50 matches. So this is how that labeling interface looks, right? So it's a very simple task for labelers where they have to look at a pivot image and they have to figure out what is the duplicate image, right? And a feedback that we have received from these people is that it's a fun game for them. So it's almost like playing a video game. So you could get this data tagged. You could also do augmentation on the top. I have already explained how you can compute negative pairs. So now you give all this data to a CIMS network, and this technique I have already explained, right? Now, after doing all these things, we got mean average precision of about 0.8, which is again not great, but it's not bad either, right? It can capture most of the duplicates that we have in our data set. So in our graph, right, so we are building a graph here, right? So in a graph now we have a duplicate relationship, right? Any questions so far? Okay. So how do we go about building a similar kind of relationship? Defining similar here is very important because the way you are going to define, machine is going to learn that way, right? So if we compare two kurtis, let's say, so the way we define is sleeves, neck, or length, these things have to absolutely match. But you can be a little less stringent on color or pattern, right? So it can still be a floral kurti, but the shape of flowers could be different. So that is all right. So you could still call those two product photos as similar photos. Similarly, in case of color, right? So we thought, look, we already have trained a network for dedupe. Why not use that network to form these kinds of links, right? So we had some evaluation data set for similar images. Now, again, we computed MAP metric, and what we found was that it was about a 0.3, which means, again, a similar image is present somewhere in the top 3 or top 4 images. And this is not acceptable. And when we saw the results, of course, since this model is trained on dedupe, so we can see that there are lots of duplicates around the pivot image. But for some reason, similar photos were pushed apart. And there were lots of non-similar items which were relatively closer to the pivot image, right? And in a way, it is intuitive because we train this model to be very strict on duplicates. So then we fell back on creating a similarity data set, right? And we use the kind of technique that I mentioned earlier, where you use a network, you filter dedupes, you take the top 50 matches, give them for labeling, get a data set, do some augmentation, and then you do a training using positive and negative pairs. So here, instead of duplicates and non-duplicates, now we have similar and non-similar, right? And again, we use a contrastive loss-based technique to train this network. So after training, when we did evaluation for MAP, it was about a 0.7. And again, it is fairly okay because the way we have defined a similarity, it also has some kind of fuzziness inherently. So now we have a similarity link between different products, okay? So remember in our graph, we have nodes and we also want to tag these nodes with consumer focused intents, right? And if you check Google Trends, there are more than 40 different consumer focused tags that you can attach with different products. And different categories will have different kinds of attributes, like tops will have college, party, casual, but kurti may have like office or Diwali or so. And secondly, casual in case of tops is not exactly same as casual in case of kurti, right? So how do we solve this problem, right? So we want to attach one of or a few of these 40 tags to every incoming product. One way is you can train a single model, which will take a photo at runtime, and then it attaches one tag out of this. Likely this is not going to work because, as I mentioned, casual in case of tops is different, from casual in case of kurti, right? Second approach is that you can have a separate model for each of these categories, right? But it might become a management headache to maintain, retrain, and then use these 30 different networks in production. So what we felt is that, look, we already have a model trained to identify similarity, right? Why can't we make use of it? So we created a data set of 50 products per tag and per category. Like if you have a sari and if you have a wedding as a tag, then we have 50 saris which have enough diversity, right? And then we said that, look, we can use this model for an incoming product. We can compute a feature vector, and then we can do a nearest neighbor search among these 50 products that we have, right? So when we observed the results, we found that it was performing okay. I mean, it was not performing bad, but it was highly dependent on the kind of pivot images that you choose. So here, for instance, in case of this sari, you have some kind of contrast between pink and off-white, right? And then it has marked most of the saris which have that kind of contrast with that tag. But there are other saris which have some similar colors, which are again falling apart from this pivot image. So again, we went back to our technique of creating a large data set out of this, right? But here it's a bit of a problem because you can't really use non-fashion experts to tag all this data, right? So you need experts, and that's an expensive task. So we did this in some kind of iteration, right? So suppose we have a deep learning model that we have trained so far. So we ask a fashion expert to have 50 new products per tag and per category, right? Then we run a model on it, and we get for each of these products, we get a new match, right? So we get the best match. So we get the best similar match. Now it may not be really eligible to be tagged with that attribute, right? So again, we use manual intervention. So a fashion expert essentially curates that. So she tells this product is tagged right, this product is tagged wrong, right? Now you can make use of this data. So the products which are tagged right, these are essentially your positive pairs. And products that are not marked as right, these are your negative pairs, right? And you can again use this data, feed this data back to the model to fine tune it, right? And this process you can repeat in iterations. And this is not an automated process, right? So here we are having a lot of manual interventions, right? So, but this was quite effective, and it took us about a month to do this process end to end with a lot of manual intervention. But at the end, we had a model which can essentially do tagging across different inspirations and across different products for 40 different tags. So now in this graph, we also have tags attached to different products. Okay, so a few observations that you also might have observed that in this, in our case, every task was different, and there were some subtle differences, and a pre-trained model on even some kind of a similar task did not work. We had to create new data set to make the model work with very high accuracy. And the models did not really generalize well, right? And we also used a lot of iterative approaches. So we gave away a lot of data for tagging. So we got that data, we did a lot of iterations. And in the end of a lot of hard work, we actually had a model which can perform reasonably well. And the fourth aspect, which I haven't gone deep into, is if you want to solve a task, you need lots of models to work with each other. So for instance, we had a separate model to identify a primary photo. We had a separate model to do segmentation, right? After that, so we got images on which we are training a few new models, right? And for every task, you need a different model. So if you really have to solve some task end to end, I think you will have to train more than one models. That's the takeaway from the fourth bullet. So at the end of all this exercise, we had we had 2 million products in our catalog. We created thousands of millions of links between these products. So in a way, with our duplicate model, we created a sensor. So we created a measurement tool which can essentially tell us how many duplicates actually exist across different e-commerce catalogs. And that number was quite staggering, like more than 30%. And in our catalog, we have more than 25% of the products tagged with the most appropriate tags. So what have we achieved by doing all these things? As I had mentioned earlier, we wish to give the best price experience to our consumers. And again, using a duplicate relationship, we have identified all the products which appear at different prices, but essentially it's the same product. We wanted to improve search results, right? So given that we now have tags with each of the products, our search engine can give a lot more a relevant set of results if you put a very intuitive query. And again, using a similar relationship, you can react to the likes or dislikes that you can get on the photos and then send the most appropriate fashion item. So I think I still have some time left, so let me just talk about some of these aspects. So I didn't really talk about the matching relationship. So I showed you earlier that we link inspirations from the web to the actual products that you can shop, right? So here again we use a deep segmentation technique where we take a photo and then we break it down at a pixel level, and then we do segmentation as well as a classification at the same time, right? So the first row shows the outputs of intermediate stages. So on the left now you have two segments of that image, and then you can do search over your entire catalog, and then you can get the most effective matches. So for this task, we had about 10,000 inspirations tagged at pixel level. Again, we created different tools, different interfaces so that people can do this kind of tagging. We had about 60,000 pairs of similar products, and it takes about half day to 1 day to train a model. And in the end, we achieved accuracy of about 75% at a pixel level, and MAP of about 0.6 for this particular task. So here we are not really searching. So we are not searching for similar items across products. So one item is image in the wild, and the other item is actually a product photo. And a funny thing is that if you use this same similar model that we have trained on a product, it actually gives a worse performance. And given that we also ingest text from different catalogs, we also have to do deep text parsing to extract tags like brand or fabric or so. Many times these are not evident on the text. So we use LSTM plus CRF kind of techniques. We have more than 20,000 paragraphs labeled at a word level. So with this data set and with some advanced techniques, we get about 95% accuracy on this task of identifying, essentially attaching different keywords to different words. Right? So that's what I had for this talk. I have 10 minutes left. So if you have any questions on any of the things that I have explained, I can answer them.
If you have questions, you can raise your hands. We'll have mics coming towards you. Yeah.
Hello. Good morning, Vijay. Can you take 2 slides before, in which that the ladies towards the end.
There are lots of ladies in the presentation. So, end?
Yeah, towards the end. Just before you closing the presentation.
Oh, okay.
Before, yes. In this one, the left side, you can see that one lady is there, and in the below, you have cropped out the t-shirt. So
yes.
This algorithm is doing cropping on its own.
Yes. So it's end to end. Yeah.
So in those movie animations and all, they use green screen, in which actor is standing in front of the green screen and they crop it using the green screen. So with this algorithm, you don't need a green screen, right? Say if I want to make a movie in which I want to use an actor, send him to Switzerland maybe. So I can simply make the actor act on any stage, use this algorithm and crop him, and use the background of Swiss Alps maybe.
Sure. So I'm not sure what kind of algorithms they use. I can definitely see fit of such techniques there. But I think it's mainly a CGI there. I think that those techniques are far more advanced than this. And I think the problem setting there is entirely different as compared to this problem, I feel. Because you have control over the settings, you can, so if you have a green screen, then you know that you have to replace only green pixels. Then it's a very simple problem, right?
Yes.
So.
Hi, here.
Yeah.
Yeah, so how have you operationalized this? So there are million of products in your catalog, millions out there on the various e-commerce portals. So let's say, how do you narrow your set for duplicate matching, and whether it's offline, online, and what is the TAT to get the results?
So in terms of operational efficiency, most of these things are done in offline manner, right? So if we have, so every day we get about 40,000 new products from different fashion portals, and we have to do a duplicate detection across, dedupe we have to do still across the entire catalog, right? And roughly it takes about 4 to 6 hours to do the entire process. So you have 40,000 new images, and you have to search over, let's say, 2 million products. So it takes about 4 hours offline.
So, as your catalog size increases, etc., do you see this being scalable?
So the bottleneck here is hardware resources. So if you have more GPU machines, this can scale well.
Hi, I'm Ravikiran. So, is training for negative cases actually required? Because when you say something is similar, there is always a definition for it, and we can tell it. But how will you tell a computer that something is not similar? It is like universal set, right? There can be anything that is not similar. And aren't we kind of misdirecting the model by telling something this is not similar and this is not similar like that?
So, firstly, negative pairs are required because if you visualize all these images in a vector space, you want to push certain products together and you want to push a certain products apart, right? So both the forces are required,
Correct.
and hence you also require positive as well as negative pairs. Uh, Now to your second question, I mean it's true that this model may not generalize well across different pairs or across different images. So in a way, we are doing it on fashion commerce data sets of Indian retailers, and I'm also not sure whether it will work on fashion photos of, let's say, US or Europe fashion portals.
Thank you.
So it's a customized thing, is what I'm saying.
Thank you.
Yeah.
Hey Vijay, here.
Hi.
Hey. So specifically, question around tags. I think tags are difficult to infer. There could be a lot of manual interventions. So what lies ahead? How can we avoid all kind of manual intervention, saying that I tag it as wedding, as casual, as outing wear? So those are prone to errors, and whenever human tries to intervene and say that I annotated that way, then our own biases come into picture, and there needs to be a lot of feedback loop to say that it actually is how customers also will perceive it to be.
Correct.
So what's your outlook on it, and what's the way forward?
So when we started looking at this problem, one challenge was that this data did not exist. So it's in a way dark data that we are creating. And to avoid bias, we take opinions of different fashion experts. So this tagging goes through multiple steps where multiple fashion experts essentially curate that. And as we are getting more and more data tagged, we can make use of that data to train better models. That's how I see it.
So first of all, a very good presentation. I think you have done a pretty incredible job. So I'm very interested in learning that some of the frameworks today that exist are such as Google has TensorFlow, then Amazon just recently launched their own deep learning. Azure already has, they also have their GPU processing as well. Is there any specific framework that you are using, or you're trying open source, or what's your thoughts around that?
So we mainly use Torch. I'm not sure if you're aware of that. Torch is being championed by Facebook.
Okay.
And when we started last year, that was one of the advanced packages that were out there. And it is still, it is still getting a lot of support. And we find it flexible because, so it's in Lua. So Lua is very fast, and it is also very easy to do core development. TensorFlow is also picking up. It's in Python, and you can also go and modify the source code also. So I see that these two are packages which are generic as well. You can do video, text, image, everything in these two packages. Cafe, for instance, I find it hard to use for text. It's very good for images and videos, but for text, it may not be the right package.
Okay. Thank you.
Yeah.
Hi, Vijay.
Yeah, hi.
Could you comment a little bit about the hardware that you have been using, like in terms of, you mentioned, right, GPUs, and those tend to be expensive, not easily available. Most of the cloud do not carry them. So how did you manage that, and what's the size, etc.?
So we have been fortunate to have support from Microsoft Azure. So they have N series, and that's in a preview mode. I think, in fact, they are going to go live this month, or I think they're already live. But we got early access to those GPUs. Those are K80 GPUs. They have 12 GB of RAM. And those work pretty fast. These are not like the really advanced GPUs, but those are fairly okay for the kind of scale that we have. And we also made use of AWS GPUs. So you will have to play with spot prices and spot instances. You will also have to change different regions to avail low prices. But whenever you have a more requirement, and if number of GPUs that you have are not sufficient, then you can always invoke those machines.
Hello. Very good presentation. I was wondering what's the applicability beyond apparel. Do you see this extended to any other categories? What would be the second category you would try?
So I feel the issues of data sets and training models will be there. These models will not generalize fairly easily. We want to go towards handbags and footwear next, and we're hoping that some of these things will be useful there. Yeah.
So Vijay, a question here.
Sorry. Where are you?
Yeah.
Yeah. Hi.
So actually, application of deep learning in computer vision is a very hot research topic in academia. I'm really impressed with how you have applied this in the fashion space. But how do you keep up to date with what's happening in state-of-the-art research, and what do you have an ongoing process? How you go about doing this?
So there are a couple of things that we do periodically. First, we have weekly or bi-weekly discussions in our group in terms of what are the new techniques that have come up in last 1 month or so. We read lots of research papers, but many times you should also take those results with a pinch of salt, because they are on limited data sets and the results are not up to the mark. So most of the research is not really production grade, and you will have to do a lot of things on the top to make it production grade. So we also identify what kind of techniques would be mature in next 6 months or so. So that's what I mean. By doing these two activities, we essentially keep track of what are the things that we can do in next 6 months.
That was the last question, Vijay.
Okay, sure. Thank you.
You can connect with him offline if you have any more questions. Ladies and gentlemen, Mr. Vijay for you.
Thank you.
Vijay, and some love for you from Flipkart. Thank you so much for being part.
Thank you.
Thank you.